I'll be presenting SAFE, which studies machine learning with shard graphs. My name is Yonatan, and this is joint work with Ben, Alessandro, Aditya, Ashwin, and Stefano. We're interested in unlearning in deep learning models. The following is a definition we use for unlearning. The definition defines unlearning as removing the effects of specific training data from the trained model. Problem is that with current paradigm of deep learning, an optimizer such as SGD or Atom will update all of the model parameters with all of the data samples and will do so over many iterations in an irreversible way. This is challenging for unlearning a particular sample, as we cannot undo all of the iterations, yet a particular sample could have been introduced at a very early iteration and is engraved into all of the data parameters. Instead, we consider compartmentalization for unlearning. Consider the typical training scenario, where we have here a data set in dark blue rectangles that is used to update a model, which we denote in light blue squares. Instead, the compartmentalized training framework will separate the data into disjoint data shards, which we can see here in the different colored rectangles, which will be used to update different parameter groups, the light orange, light blue, and light yellow. With this framework, we're able to train a model with separate shards of data. This is desirable for unlearning because suppose we want to unlearn a particular sample. Suppose the fourth sample from the bottom we want to unlearn. In traditional training, we would actually have to retrain the entire model on the entire training set. This is because that sample was engraved into all of the model parameters in an irreversible way. However, in contrast, in the compartmentalized training setting, if we want to forget that same sample, we would only have to retrain the corresponding parameter group, and would only have to retrain it with a particular dataset shard. This makes compartmentalized training an order of magnitude cheaper when we have a large number of shards. This leads us to the data sharding trade-off. As we said, in compartmentalized training, we split the training data into disjoint data shards that are used for this updating disjoint parameter groups. But we get into the sharding trade-off. We can train with a very large number of shards. Now, if we split our data into a large number of shards, the number of samples in each shard will be small, but the model accuracy is going to be low. We're going to achieve very cheap unlearning since each data shard is going to be very small, but the accuracy is low since each model shard will be optimized with a small amount of data. In contrast, we can train with few shards, which will be expensive to unlearn, so the number of samples in each shard will be high, but this will lead to higher accuracy. We argued that this is because when training with many shards, the number of samples in each shard is small, which results in a loss of synergy, even if we assemble all of the trained shards after training. And we present SAFE to elevate this issue. SAFE stands for Synergy Aware Forgetting Ensemble. And in SAFE, we alleviate the data sharding trade-off by harnessing shard synergies. SAFE creates shards that harness synergy by the construction of a shard graph. A shard graph relies on a shard topology to define which shards are used to train a particular parameter group. So the classic sharding can still be considered in this framework. This will be the example of the isolated shard. But we can actually use the framework for much more flexible sharding, where you can define a particular parameter group to be trained with a set of shards using all nodes and outbound connections from a particular shard node. This makes forgetting more intricate. So now if we want to forget a particular sample here, A, we'd have to consider also additional parameter groups that use it in its training. But overall, this enables us to train with much larger number of shards, and we get faster retraining accuracy. As we said, training with SAFE enables us to train with much larger number of shards. But training with large number of shards requires that we train, store, and run inference on, in some cases, hundreds of models, which are trained on the different shards. If we do this naively and assemble the models, this will be prohibitively expensive. So we'll have to run inference on hundreds of models for each prediction. Instead, we propose to use Inca adapters, which were introduced in Ducler et al., which enable us to construct distinct models that share the computation of the pre-trained backbone. This is the architecture of the Inca adapter. It uses a pre-trained backbone, here in light blue, which is frozen, and extract intermediate activations of the backbone to train independent adapter models. These adapter models are trained independently and are not fed back into the network, which enables us to share computation both during training and inference, which makes the inference very cheap, as comparable as running just a single large backbone. Overall, we conclude that we present SAFE that compartmentalizes a dataset to hundreds of shards according to the notion of the shard graph. We show that using the shard graph, we're able to use a finer set of shards and achieve state-of-the-art results in unlearning by harnessing synergies of the shard graph and remaining highly efficient using the Inca architecture. If you'd like to learn more, check out our poster on October 6th in the AM session.